This is lecture 21 in BBSP 610. We'll be discussing analysis of variance, otherwise known as ANOVA. First, just to give a general overview of when you would want to use ANOVA and when you would want to use other methods that we've discussed in this class. One of the most common questions you want to answer using statistics is to see if two variables are related to one another somehow. If there's some type of association, can you use one variable to explain or predict the other variable? If so, is the association stronger than we would expect to observe due to chance? And just how strong is this association? Let's say you have two categorical variables that people either get a drug or a placebo, or they have pain relief or no pain relief, and you want to test the null hypothesis. There's no association between drug slash placebo and pain relief. Or is smoking related to lung cancer, or is race related to the risk of developing chronic pain after a car accident? In that case, you would use chi-square tests, or proportion tests, or Fisher's exact test. If you have one quantitative variable and one binary variable, say, for example, you administer a treatment to mice and a placebo to mice, and you want to know if it affects their weight, or you want to know if smoking affects a baby's birth weight, or does two different types of tumors have an effect on gene expression. In these cases, you'll want to use t-tests or non-parametric tests such as bootstrapping. And if you want to see if there's an association between two quantitative variables, say between age and pulse rate, or between time and infant mortality, then you would use some form of regression, multiple regression, single regression, to test the null hypothesis of no association between the two quantitative variables. Well, today we're going to discuss one other case that we haven't considered up till now, when you have one quantitative variable and one categorical variable that's not binary. That, if you remember the insect sprays example from the second homework assignment, say we want to test the null hypothesis that all 6 insect sprays are equally effective. Or say we measure the number of people who develop a certain disease in different races, we want to test the null hypothesis that all races are equally likely to develop the disease. Or say we have 3 different plates with different conditions, we want to see if cells grow at the same rate on each of these plates, then we can use analysis of variance, more commonly known as ANOVA. ANOVA, when you're comparing exactly two groups, you can show ANOVA is essentially equivalent to a t-test. And as you'll recall, with the t-test, we're testing the null hypothesis that two groups have the same mean. And with ANOVA, we're testing the null hypothesis that 3 or more groups have the same mean. That raises the question, why do we need ANOVA in the first place? Why don't you just take a t-test and do it several different times? Well, in theory, you could just take every possible pair of variables and do t-tests on every possible pair of variables. In practice, there are several reasons why you don't want to do this. First of all, as we've discussed before, there's a problem with multiple comparisons. Say you have 10 different groups and you want to test the null hypothesis that the means are the same in all 10 groups. Well, that would require you to perform 45 t-tests. That would be a pain in the butt for starters, and it would also mean that the probability of type 1 error is much greater than 0.05. If you use a 0.05 threshold for significance, you would have to use a more stringent threshold. That could cause you to lose power. In general, it's something that you want to avoid. There's other reasons to prefer ANOVA as well. As I alluded to on the previous slide, it can give you better power. That if you use ANOVA and you want to test the null hypothesis that all the means across all the groups are equal, you'll get much better power for that than if you just did a bunch of pairwise t-tests. And also you may want to consider group structure. Say you have 2 different types of drugs and a placebo, and you want to compare the drug group to the two placebo group, or the placebo group to the two drug groups combined, there's not a good way to do that using t-tests. I mean, I suppose you could pool them, but that creates other problems. That's relatively easy to do using ANOVA. So, the general ANOVA model in mathematical terms is the following, that if observation I belongs to group K, then yi, the value of the observations I, is equal to mu plus tau sub k plus epsilon sub I, where mu is the overall mean, tau sub k is the offset for group K, and epsilon I is the error for observation I. In general, tau k, you can think of that as the difference between the mean of group K and the mean of all the groups combined. Under the null hypothesis, all groups will have the same mean, so all these offsets will be equal to 0, and the mean in each group will be equal to the mean for the full sample. The alternative hypothesis is that there's some non-zero tau sub k, implying that one of the groups has a different mean than the overall group mean. So we can view ANOVA as a special case of a regression model, and to me that's the simplest way to think of ANOVA. There's other ways to do this, as I'll discuss in a few minutes, but I prefer to just think of it as a regression model. That for each observation yi, I define a series of variables x sub ki, such that it's equal to 1 if observation I is in group K, it's equal to 0 otherwise. X sub ki is known as a dummy variable. For example, if these were dummy variables for race, if subject I in your study, if, say, X1 is a dummy variable for Caucasian race, if participant I in your study is Caucasian, then the dummy variable is equal to 1, otherwise it's equal to 0. And if you have another dummy variable for African American, once again, if participant I is African American, it will get a 1, otherwise it's equal to 0. So to do this ANOVA test that I just described, we can fit the following multiple regression model where we let yi equal to b0 plus b2 times xi2 plus b3 times xi3, where the xi's are dummy variables defined as on the previous slide, and testing the null hypothesis that tau sub k is equal to 0 for all k under the null hypothesis is equivalent to testing the null hypothesis that b sub k is equal to 0 for all k in this regression model. As you'll recall, we've done this before with a regression f-test, so we've basically solved the problem. Now, if you're paying attention to the previous slide, you might think that there's a typo there, that there was no b1. That was actually deliberate. The reason I didn't include b1 in the previous equation is because if I had included it, the model would be perfectly collinear and there would no longer be a unique solution to the regression equation. If you tried to do this in R, it would give you an error message. So the convention is to treat the first group as the baseline and compare all other groups to the first group. Usually you choose your baseline in a logical manner. For example, if you're comparing 3 different types of treatment to a placebo, you would let the placebo group be your baseline group, and then you would compare the other 3 groups to the baseline. So here's an example with the data set that was contributed by a former student in this class. She was measuring GSH, which I assume is some type of chemical. I actually don't know what that stands for. It was produced by cells measured after 5 days in concentrations. There were 3 different groups: the control group, the vehicle group, and the treatment group. As I understand it, the vehicle group is another type of solvent that was used to transport the treatment, but it did not actually contain the treatment. We want to test the null hypothesis the GSH concentration was the same in all 3 groups. Well, I've posted this data set on Sakai. You can read it in and try this yourself if you want, and you can do it using the lm command. And GSH is the column in this data set called GSH is just the GSH level for each sample. Group has 3 possible values. It's either control, treatment, or vehicle. And you can see the output here that treatment has a coefficient of minus 0.24 and the vehicle has a value of minus 0.12. So we conclude that the GSH levels are lowest in the treatment group and the vehicle group is significantly lower than the control group. We can't directly compare the vehicle and treatment groups using this output. I'll explain how you can do that comparison here in a minute, but it looks like both the vehicle and the treatment lower the GSH levels. In general, in R, LMY Whittle X will fit in an ANOVA model if X is a factor. R will automatically convert X to dummy variables, so you don't have to worry about that. So, going back to this output, the way you can interpret this, see intercept is equal to 0.4475. That tells you that the mean level of GSH in the treatment group, or is in the control group rather, is about 0.4475. To get the estimated GSH level in the vehicle group, it would be 0.4475 minus 0.11875. You just add the coefficient for vehicle to the intercept. Likewise, to get the estimated GSH levels in the treatment group, it would be 0.4475 minus 0.23875. This slide basically just illustrates what I just said. In the control group, the mean GSH level is 0.4475. To get the mean levels in the vehicle and treatment group, you subtract their coefficients from the intercept coefficient. We conclude both the vehicle and treatment group have a significantly lower concentration than the controls. For an ANOVA model to be valid, 3 assumptions have to be satisfied. The data has to be approximately normally distributed, the data have to be independent, and the variances must be the same in each group. In practice, these assumptions can be violated and bad things usually won't happen. If they're not independent, then you're screwed. You really need the data to be independent. There's ways to deal with this if they're not independent, but we're not going to discuss them in this class. You can talk to me if you'd like some additional information about that, but for the purpose of this class, they have to be independent. The normality assumption is just like it is in the case of the t-test, that if you have a small sample size with really bad outliers, then the lack of normality can be an issue. But in the vast majority of cases, the central limit theorem will save us, so it's rarely a big deal. And the theory behind ANOVA also assumes that the variances of the groups are equal. And in principle, you can get inaccurate results if the groups have drastically unequal variances. In practice, it's almost never a problem. The rule of thumb is the ratio of the standard deviation of the largest standard deviation to the smallest standard deviation is less than 2, then it's probably fine to use ANOVA. In practice, even that rule is probably overly conservative if the ratio is greater than 2. Even then, it's usually only a problem if the sample sizes are small and unequal. But if all these things go wrong at once, if the sample sizes are unequal, one group is much larger, much smaller than the others, and and one of the groups has much larger standard deviation than the others, and none of the groups have a particularly large sample size, then ANOVA can get messed up. But in practice, people usually don't even bother to check this because it's very rare to get into problems when the variances are unequal. I'll explain to you how to do this just in case you ever get a reviewer who throws a fit over this. But in practice, I never even bother to check this assumption unless you have unequal sample sizes and a small sample size overall. So one way you can do this is to just compute the standard deviations directly. And this case, I can use the SD command, GSH bracket group equals control equals vehicle or treatment, whatever. I see the controls have the largest variance, the treatment group has the smallest variance. I take the ratio and it is a bit on the large side. So it's a potential concern here, but I'm not going to lose too much sleep over it given that the groups, the sample size are approximately the same across the three groups. If you'll recall from earlier commands, in general, if you say y and then brackets x equals level, that'll return all the elements of y where x is equal to level. So in this case, it gives the concentration for the control, vehicle, and treatment groups. Another option is you can plot side-by-side box plots like you see here. We did this in the second homework assignment. I won't bore you too much with all the details, but you can see that the bands for the treatment group are much smaller than controls or vehicle. Again, potential cause for concern. I'm not too worried about it given the equal sample sizes. If in case you've forgotten, you can do side-by-side box plots using the command boxplot Whittle X. If you don't see evidence that some of the IQRs are significantly wider than the others, then we can conclude that the ANOVA model is valid. Another way to do this is to produce something that's called a scale location plot that I won't explain. This is basically for each possible fitted value, it shows the square root of the absolute residuals. The basic idea is that if the fit of your model is good, this line should be more or less flat. In this case, you can see it does increase for the vehicle and treatment groups. The vehicles in the middle here, or the vehicle and control groups, rather, the vehicles in the middle and controls on the right. So, cause for concern, but hopefully not too big of a deal. In general, if you have an LM object, you can feed that object to the plot command if you want to get a scale location plot. And if the ANOVA assumptions are satisfied, the scale location plot should be flat. Now we'll briefly discuss how you can do pairwise comparisons. As I said before, ANOVA allows us to test the null hypothesis the means are equal in all the groups. And the summary.lm command gives the p-value for testing the null hypothesis that there's no difference between each group and the baseline group. And a lot of the time that's all we care about, but sometimes we may want to compare two non-baseline groups. Say, like for example, we may want to compare the vehicle group to the treatment group. If you do this, you have to adjust for multiple comparisons. One way to do that without losing too much power is what's known as Twokey's honest significance difference method. I won't describe the method in too much detail. Suffice it to say, it tries to do this while minimizing the loss in power. Basically, it creates confidence intervals for each possible set of pairwise differences while taking the multiple comparisons into account. So the intervals are chosen such that there's a 95% probability that all of the intervals contain the true mean differences. So here's the syntax for the Twokey HSD command in R. You'll notice here I say Twokey HSD, AOV, GSH twiddle group. Note that I use AOV rather than LM. AOV also does analysis of variance in R just like LM does. I usually prefer LM because it gives you output that's easier to read and interpret, but AOV does the same thing. The reason I use AOV here is because Twokey HSD requires you to feed it an AOV model. If you feed it an LM model, you'll get an error. So what this tells us, if I give the output of gsh.twokey, the difference between treatment and controls we saw earlier is 0.23875. The p-value is tiny here, very strong evidence of a difference between those two groups. Likewise, the difference between vehicle control is 0.11875 as we saw earlier, and the difference between vehicle and treatment is 0.12. In each of those cases, the p-value isn't quite as tiny as we got for the treatment control pair comparison, but it's still very small. We conclude that the vehicle and the treatment groups differ from one another, as do the treatment control and vehicle control groups. And you can see this graphically using the plot command. You'll see it on the next slide, that this output here shows all possible pairwise comparisons and a 95% family-wise confidence intervals for the differences. These confidence intervals should not cover 0 if the difference is statistically significant. See, none of them do, which is consistent with what we saw on the earlier slide. So in general, Twokey HSD of an AOV object creates a set of confidence intervals for the mean differences of each possible pair of factors, such that there's a 95% coverage probability for all the intervals combined. You can modify the coverage probability using the conf.level parameter. Most of the time in practice you won't, but you can. And AOV, as I said before, fits an ANOVA model, testing the null hypothesis. The mean of y doesn't vary with respect to the different groups in X. I prefer LMY Whittle X since it gives you more informative output, but for Twokey HSD you have to use the AOV command. So things to remember for today's lectures: you can use ANOVA to test the null hypothesis that 3 or more groups have the same mean. It's a special case of regression by using the appropriate dummy variables. It depends on various assumptions, including the assumption that the variances are equal, though in practice independence is the one that's most likely to give you problems. And if you do a bunch of pairwise differences, you should adjust for multiple comparisons using Twokey HSD or other methods. Our commands for today is LMY Whittle X will fit in an ANOVA model, AOV is an alternative method, and Twokey HSD will calculate pairwise differences from an ANOVA model.